Okay, so our question is, again, if you increase the temperature of a mole of a gas by delta T, what happens to the total kinetic energy of the gas? Well, the change in kinetic energy is going to be the kinetic energy after the increase minus the kinetic energy before the increase, which is what? 3/2 K times T plus delta T, being the kinetic energy if the temperature becomes T plus delta T, minus the 3/2 KT that you started with before the delta T. And very simple arithmetic, the 3/2 KT is going to divide out here, and you're going to end up with 3/2 K times delta T, so that the kinetic the average kinetic energy increases by 3/2 K delta T. Well, what does that do to the total kinetic energy in the mole? Well, in the mole you have Avogadro's number of particles, so you multiply the kinetic energy increase of the average single particle by the number of particles, and you get this. K times Avogadro's number is R, so you have 3/2 R delta T. Now, to get the total kinetic energy of the particles in a mole of an ideal gas, we take the kinetic energy 3/2 KT of single particle, multiply that by Avogadro's number, the number of particles in a mole, and we get 3/2 RT. So that the total kinetic energy of particles in n moles of a gas is 3/2 nRT. Now, we note that 3/2 nRT is 3/2 product of pressure and volume, because of course PV equals nRT, the ideal gas law. So now we have a simple way, and I see that I made a mistake when I did this. Let's correct that. Okay, for example, if you have 1/2 liter of gas, which is about what you would have in this bottle, at 100 kilopascals atmospheric pressure, approximate atmospheric pressure at this altitude, then the kinetic energy is going to be 3/2 PV. I left the 3/2 out when I wrote this earlier. It's 3/2 PV, which is 3/2 of 50 liters times kilopascals, half a liter times 100 kilopascal, liter being 100th of a cubic meter, kilopascal being 1,000 cubic meters. We end up with newtons per square meter multiplied by cubic meters, or Newton meters, which is joules, and we get 75 joules, total kinetic energy of the particles in the gas that occupies this bottle. Okay. Now, what we call the total translational area, total translational kinetic energy, is the total kinetic energy. This is really total translational kinetic energy. Our model previously was just single particles moving around, bouncing off of each other, and so forth. That's not the way most gases are constituted. Air, for example, is constituted of diatomic oxygen molecules and nitrogen molecules. Oxygen molecules, I say, look like this, two separate masses, and they're actually not held together by a little bar or string. They're held together by electrostatic interactions. And in reality, these molecules have a mass concentrated in a very small nucleus with a few electrons around that nucleus. The electrons don't have very much mass, so it's almost like 2 point masses separated by a large distance. The distance between the nuclei is tens of thousands times the size of a nucleus. So in any case, we can think of this dumbbell type molecule. Okay, this molecule can rotate about 2 independent axes. If we show the molecule here, and of course the molecule could be at any angle, we can impose a coordinate system where one of the axes is coincides with the axis 3 through the centers of the two molecules. We can't have a rotation of that dumbbell-shaped molecule about this axis, but we can about the two axes perpendicular to this axis, the two independent directions perpendicular to the direction of this axis. And we could really go into much more detailed explanation, but what we see is that the molecule can rotate about two independent axes. We can't have rotation about this axis. The molecule can't really spin like this, but it can rotate like this. Okay? Now, this means that in a diatomic gas and air being very much diatomic, that the kinetic energy is distributed among the x, y, and z directions in a manner that we've already seen, the x, y, and z kinetic energies being on the average equal to one another, but also among two modes of rotation. So that instead of splitting the kinetic energy among just three directions, we're splitting it among 5 modes. Motion in the x direction, motion in the y direction, motion in the z direction, motion about each of two independent axes of rotation. It's going to turn out that the kinetic energy distributes itself evenly among these modes, so that for every bit of energy in the x direction, every bit of energy in the kinetic energy in the x direction, we have an equal amount of energy in the direction of the two in each of the two modes of rotation. So the question that we go on next is just what are the implications of this for the amount of energy you have to put into a diatomic gas to increase its temperature. We know how much energy we have to put into it to increase the translational kinetic energy of the particles, but how much to also increase the rotational kinetic energy.